Okay, welcome to the deep dive. We are plunging into something surprisingly fundamental today, something literally right under our feet. We're talking about Earth's density. And here's the thing that grabs you right away. Earth is actually the densest planet in the whole solar system.
It really is. It feels a bit counterintuitive when you first hear it, doesn't it?
Yeah.
You think about Jupiter, Saturn, these massive gas giants. You'd kind of expect the biggest to be the densest.
Right. Like packed tighter.
Exactly. But nope. Earth holds that title. Most compact, pound for pound, out of all the planets.
Absolutely. And the source material we've pulled together for this deep dive, it really helps us get, well, under the surface, you could say.
Yeah, literally.
To unpack why. Why is Earth so dense? And what does that really tell us about our cosmic neighborhood?
So yeah, our mission today is figuring out what makes our home planet so uniquely packed together.
Let's get into it. What's the actual number?
Okay, so the average density, according to the sources, is about 5.51 grams per cubic centimeter.
5.51?
Yeah. And just for context, like water is 1 gram per cubic centimeter.
Okay.
So Earth is, on average, over 5.5 times denser than water. It might just sound like a number, but that's really high for a planet.
It really is. And it makes you wonder, again, about those huge gas giants. How does our, relatively little rocky planet end up denser? What's the trick?
It's mostly about what's inside Earth. Its structure, its composition. Earth isn't just a solid ball, right?
No.
It's layered.
Right, the layers.
And the real reason for that high density is deep down. It's the metallic core.
Ah, the core. That super hot center we all learn about. Iron and nickel, right?
Exactly that. Both parts of it, the solid inner core and liquid outer core, they're mostly this really, really dense mix of iron and nickel.
So like a giant metal ball bearing at the center.
Kinda, yeah. Think of it like a huge heavyweight right in the middle of the planet. This central region has so much mass packed into its volume, it just pulls the overall average density way, way up.
Okay, so even though we have like the mantle, which is rocky and less dense,
Silicate rocks, yeah.
and the crust on the very outside, which is even lighter, that super heavy core just dominates the average.
Totally dominates. The core is something like a third of Earth's total mass, but it's only about 16% of the volume. So you see that concentration of heavy stuff. Huge factor.
Wow, okay. A third of the mass in such a small part of the volume. Is that everything, though, or is there more to it?
There is another piece, definitely. It's gravitational compression. Yeah, the planet's own gravity. All that mass pulling inwards towards the center creates these unbelievable pressures deep inside.
Just squishing everything.
Literally squishing it.
Yeah.
It packs the atoms and molecules tighter together than they'd normally be. So this compression boosts the density through the whole planet, really, on top of just having that heavy core.
Got it. So it's a double whammy. A really dense core plus gravity squeezing everything tighter. That makes sense. So, okay, how does this setup compare when we look out at the other planets?
This is where the picture gets really clear. It shows just how, special Earth is in this way. Let's run through the numbers from the sources. Earth, we said, 5.51 grams per cubic centimeter.
Right.
Mercury is next. Pretty close, actually, 5.43.
Oh, interesting. Almost the same.
Then Venus, 5.24. And Mars is quite a bit lower at 3.93.
Okay, so the rocky planets, the ones kind of like Earth, they're next in line, density-wise, but all lower than Earth. Mercury's really close.
Very close. But then you move out to the gas giants, and there's this massive drop, like a cliff.
Okay.
Jupiter's 1.33.
1.33 compared to over 5 for Earth. Big difference.
Huge difference. And then Saturn. Saturn is 0.69.
Whoa, hold on. 0.69.
0.69.
That's less than 1. That's less dense than water.
Exactly. That's where you get that famous kind of mind-bending example, right?
The floating planet.
Yeah. If you could find a bathtub big enough for Saturn, which, you can't. But if you could, it would float.
That's incredible for something so enormous.
It just perfectly shows the difference. These gas giants are mostly hydrogen and helium, really light stuff, even squished down, whereas the inner planets are rock and metal. Heavy stuff.
Okay, finish the list. Uranus and Neptune.
Right, Uranus is 1.27 and Neptune is 1.64. So denser than Saturn, but still way, way less dense than the rocky planets.
So they're all hovering around like 1 to 1.5 times the density of water, roughly. Except Saturn, the outlier.
Pretty much, yeah.
And back to Mercury for a second. You said it's almost as dense as Earth. Why is that one so high, being smaller?
Good question. It's a similar reason to Earth, actually. Mercury seems to have a surprisingly large iron core for its size.
Oh, okay. So a big engine in a small car, sort of.
That's a decent analogy, yeah.
Right.
Its core makes up a bigger percentage of the planet than Earth's core does, relatively speaking.
Okay.
That large, dense core boosts its average density way up, making it number 2.
So this isn't just like a random collection of densities. This pattern-dense inner planets, fluffy outer planets, it means something bigger.
Oh, absolutely. Yeah. It's fundamental. This density difference is basically a fossil record of how the solar system formed.
How so?
Well, think about the early solar system. Close to the young sun, it was hot. Only materials that could stand the heat-heavy things like iron, nickel, silicate rock could condense into solids.
Building blocks for the inner planets.
Exactly. They clumped together to form these dense, rocky whorls. But further out, where it was much colder, lighter elements, the gases like hydrogen and helium and ices, they could survive and stick together. And there was just way more of that stuff available overall. So they built up these enormous but low-density gas and ice giants.
So density is like a historical marker, tells you where and how the planet formed.
In a big way, yes. It reflects the temperature gradient and the materials available in the early solar nebula. Density isn't just a number, it's like a planetary birth certificate.
Okay, let's wrap this up. Summing up this deep dive, Earth wins the density contest.
Top of the charts, yeah.
And the main reasons are that massive, super dense iron nickel core deep inside, plus the incredible squeeze from gravity packing everything down.
Making it much denser than the other rocky neighbors like Venus or Mars, and way denser than the gas giants.
Especially Saturn. Can't get over that floating planet image.
It really sticks with you, right? 0.69 GCM. Astonishing.
So why is this fascinating for you, the listener? Why should you care about grams per cubic centimeter?
Well, because understanding Earth's density gives you like an X-ray view into our own planet's heart. It's key evidence for what's deep inside where we can't go.
Right. It tells us what we're made of, fundamentally.
And it places us, it places Earth in the grand scheme of things. It shows you the amazing variety just within our own solar system, how different planets can be, all born from the same cloud of stuff.
It really does make you stop and think. This huge range, Earth being so compact, Saturn being almost, well, airy. Just among our neighbors.
Yeah.
What does that huge range of densities tell us about all the other types of worlds that must be out there in the universe? And, what other secrets, what surprising things might be hiding inside these planets we're only just starting to really explore?
Yeah. Plenty more to discover, for sure.
Definitely something to think about until our next deep dive.